Howdy. This video is on electrochemical cells. By combining two half reactions in two separate beakers, we can create a cell and can convert chemical potential energy into electrical energy or electrical energy into chemical potential energy. To convert chemical potential energy to electrical energy, we need to force the electrons to go through an external wire, which is why electric cells are composed of two compartments. After watching this video, you should recognize that potentials of half reactions cannot be determined independently or in absolute terms, hence are defined relative to the standard half cell, which is defined as having a zero potential. You should be able to determine if a reaction can be used as a voltaic or galvanic cell. I'll use voltaic and galvanic interchangeably, or an electrolytic cell. You should recognize that the chemistry is the same if one beaker is used or if two beakers are used. You should be able to describe how a cell and its components, for example, a salt bridge, work, and you should be able to write and interpret cell notation. And so given the two reduction half reactions and their corresponding potentials, we should be able to determine which of these two reactions are spontaneous. Now, if we look at that first reaction, we have zinc ions plus copper metal. And so zinc ions here, so we don't have to flip this reaction. And so that gives us a minus 0.76 volts. Now here the copper metals reactant, here's the product, so we'll flip this half reaction to give us a minus 0.34. And so if we add those two half reactions, we'd get a negative 1.1. And so this reaction will be non-spontaneous. The second reaction is the first one with the products reactant switched, and so this one will be spontaneous. And so we have a 1.1 volts for this bottom reaction corresponding to it being spontaneous.
When a strip of zinc metal is immersed in an aqueous copper-2 sulfate solution, electrons are transferred from zinc to the copper-2 ions. Copper metal deposits on the zinc strip and collects at the bottom of the flask. Zinc atoms are oxidized to zinc-2 ions, which enter the solution. This spontaneous oxidation-reduction reaction is summarized in the chemical equation shown.
And so it's kind of cool. If you put a hunk of zinc in a solution that has copper ions, you'll actually end up with zinc ions and some copper metal. Because it's a spontaneous process, that means we should be able to use it to convert chemical potential energy into electrical energy. Now, if we want that electrical energy, we have to force the electrons to go through an external circuit. So we did this reaction initially in a single beaker, copper ions with zinc metal. Now if we separate out to two half reactions, so here we have the zinc metal, zinc ions, and copper metal, and so the chemistry is exactly the same. We're still going to go from copper ions to copper metal and from zinc metal to zinc ions, but again we're going to force those electrons to go through an external circuit.
Copper-zinc oxidation-reduction reaction can be made to yield useful electrical work by incorporating it in a voltaic cell. The zinc electrode is immersed in a solution of zinc sulfate. The copper electrode is immersed in a solution of copper-2 sulfate. No current flows through the light bulb because the electrical circuit is not complete. To complete the electrical circuit, we add a tubular bridge filled with aqueous sodium sulfate solution with a porous plug on each end. We now have a complete circuit and current flows. When we replace the light bulb with a voltmeter, we find that the cell has a potential or voltage of 1.1 volts. The copper electrode is the positive electrode, and the zinc electrode is the negative electrode. As the cell reaction proceeds, zinc atoms of the zinc electrode lose electrons and move into the solution as zinc ions. At the same time, copper-2 ions acquire electrons at the copper electrode and form copper metal. The reaction in the left-hand compartment is oxidation of zinc. The electrode at which oxidation occurs is called the anode. The reaction in the right-hand compartment is reduction of copper. The electrode at which reduction occurs is called the cathode. Electrons flow from the anode to the cathode through the external circuit. To maintain electrical neutrality in the two cell compartments, ions must move through the salt bridge. In summary, remember that in a voltaic cell, the anode at which oxidation occurs is the negative electrode. The cathode at which reduction occurs is the positive electrode. Electrons flow through the external circuit from
And so it's really kind of cool. The measured voltage was actually equal to the voltage that we calculated here. And it's a little confusing. This looks kind of complicated. You got two beakers, you got the salt bridge, a couple of electrodes, but the chemistry here is exactly the same as the chemistry in a single beaker. So please remember, standard potentials of half reactions cannot be measured directly or independently, and so they're always measured relative to the standard half cell, which is defined as having a zero potential. And so again, typically you're given the reduction half reactions and the reduction potentials. If you want the oxidation, you just flip it. And so these are reductions. Remember, Leo goes GER, lose electrons oxidation, gain electrons reduction. And so for reduction half reactions, you always have the electrons as reactants. And now if we flip these, we have electrons as products, and so these are oxidation potentials. And for electrochemical reaction, you always need an oxidation half reaction and a reduction half reaction. Electrochemical reactions, you just have transfer of electrons from one thing to another thing. Now sometimes this equation is used in textbooks or movies. The cell potential is equal to the reduction potential at the cathode minus reduction potential at the anode. The anode is where oxidation occurs. And so minus reduction potential at the anode is the same as the oxidation at the anode. And so I think it's a little bit easier to understand that the cell potential is equal to the reduction potential plus the oxidation potential. So I always do it this way. Your textbook, I think, actually does it this way. Some things you may see on the internet does it this way. But again, these two are equivalent because at the anode you always have the oxidation, and minus reduction potential is equal to the oxidation potential. And so we can determine the potential of the reaction by just combining the potentials of the half reactions.
Cell potential of a voltaic cell, such as this zinc-hydrogen cell, can be thought of as the sum of two half-cell potentials. Under standard conditions, the cell potential, E0, is the standard reduction potential of the cathode, minus the standard reduction potential of the anode. We can assign half-cell potentials once we settle on a reference half-cell potential. That has been chosen as the hydrogen half-cell with 1 molar aqueous hydrogen ion and 1 atmosphere pressure of hydrogen gas. For the zinc-hydrogen cell, the measured standard potential is 0.76 volts. And the standard half-cell potential for the cathodic half-cell is defined as 0. Thus, the standard half-cell potential for the anodic half-cell is minus 0.76 volts. This is the standard reduction potential for the reduction of zinc plus 2 ion.
And so it's kind of cool. All you have to do is, if you want to measure the half-cell potential for a half reaction, couple it with the standard half-cell, and then you just measure it. And so in this case, we're looking at the oxidation of zinc. The measured potential for the cell is 0.76. And so that means the oxidation potential for the zinc must be plus 0.76. I also should have mentioned that oxidation always occurs at the anode. Reduction always occurs at the cathode. You can remember this by oxidation and anode start with vowels. Reduction and cathode start with consonants. And so during the reaction, the zinc electrode actually gets lighter, and the hydrogen gas is produced.
As with all voltaic cells, the zinc-hydrogen cell consists of two half-cells. On the left is the zinc-zinc ion half-cell. It consists of a zinc electrode, immersed in a 1 molar aqueous zinc nitrate solution. The hydrogen-hydrogen ion half-cell consists of an electrode made from a non-reacting metal, such as platinum, over which hydrogen gas at 1 atmosphere pressure is passed. The electrode is immersed in a 1 molar solution of nitric acid. A salt bridge of sodium nitrate solution completes the electrical circuit. In this voltaic cell, the zinc electrode serves as the anode, the electrode at which oxidation occurs. The platinum electrode on the right serves as the cathode, the electrode at which reduction occurs. When the lamp is replaced by a voltmeter, the cell potential measures 0.76 volts. Electrons flow from the zinc anode through the voltmeter to the hydrogen electrode, which is the cathode. As in any voltaic cell, The anode is the negative electrode, and the cathode is the positive electrode. Zinc-2 ions are formed at the zinc electrode. At the same time, hydrogen ions are reduced to hydrogen gas at the platinum cathode. In this molecular level view, the hydrogen ions in solution are represented as the hydronium ions, the form in which the protons exist in solution. When a hydronium ion contacts the surface, an electron is transferred and a hydrogen atom is formed. The water molecule moves off into the solution. Hydrogen atoms formed on the surface migrate and eventually combine with another H atom to form molecular hydrogen, which bubbles from the surface.
And so again, notice that for the standard half cell, typically platinum is used because platinum is not very reactive. Platinum is not in your half reaction. It doesn't participate in the reaction. It's not consumed or produced. It's just where the reaction occurs. And so here we have two more half reactions. And if we add these two half reactions, we can get this one or this one. If we look at the top one, we have O2, O2, so that would be plus 1.23. And if we look at the next one, we have H2O, so probably going to have to flip that one. And so that would make it a plus 0.83. And so if you add those two, that gives you 2.06. And so this top reaction is going to be spontaneous. And the bottom reaction is non-spontaneous. Now we can ask ourselves, is there any way of forcing this reaction to occur? It's non-spontaneous, it has a negative potential, a positive delta G naught, and your K is less than 1. Well, if we apply a voltage greater than 2.06, we can actually force this reaction to occur. This is just the electrolysis of water.
The decomposition of water is thermodynamically disfavored, but can be made to occur by electrolysis, the application of an external electric current. Here, platinum electrodes transfer electrons between two cell compartments to separate the decomposition products. Gaseous oxygen rises from the anode at the left, hydrogen from the cathode at the right.
So it's kind of cool. If you look at the stoichiometry, you're going to produce twice as much hydrogen gas as oxygen gas, and that's what it looks like here. You probably have twice as much hydrogen gas as oxygen gas. And so if the potential is negative, you can form an electrolytic cell, which means that you add electrical energy and you're producing chemical potential energy. If your potential is positive, then you can form a galvanic cell, converting chemical potential energy into electrical energy. And so again, the reaction is just occurring at the electrode. And so electrolysis of aqueous sodium chloride is actually used to produce sodium hydroxide and chlorine gas. So the reaction at the bottom, you have a negative potential, which means you can use it to form a electrolytic cell. It's really kind of interesting. Charles Hall developed the electrolytic process to produce aluminum metal and founded Alcoa. Alcoa is actually still a company that is used to produce aluminum. Before this process was discovered, aluminum was a very rare metal and wasn't used in many things. And so if your potential is positive, that means your delta G naught is negative, K will be greater than 1. It's product favored. It's a spontaneous process, and it can be used for voltaic or galvanic cell. Again, voltaic, galvanic, I'll use those two terms interchangeably. If your potential is negative, then delta G naught is going to be positive. It will be a non-spontaneous process. Your K will be less than 1. It's a reactant-favored process, and you can use it for electrolytic cell. For a galvanic cell, you're converting chemical potential energy into electrical energy. For electrolytic cell, you're converting electrical energy into chemical potential energy. Oxidation always occurs at the anode. Reduction always occurs at the cathode. Again, oxidation and anode both start with vowels. Reduction and cathode both start with consonants. And so galvanic cells are based on spontaneous reactions. Again, they'll have a positive E naught, a negative delta G naught, and K will be greater than 1. For electrolytic cells, they'll have a negative E naught and a positive delta G naught, and K will be less than 1. And so it's kind of interesting. A rechargeable battery actually functions as a galvanic cell when it's doing work and an electrolytic cell when it's being charged. And so if you think about your car battery, when you start your car, what's happening is energy is going from your battery to the starter motor, which is trying to rotate the engine. And so the battery is behaving like a galvanic cell. As you're driving, a belt in your engine is rotating the alternator, which is recharging the battery. And so as you're driving, the battery is behaving like an electrolytic cell. Now, inside your lead battery, there's actually 6 galvanic cells. Each have about 2 volts, and so that gives you a 12-volt battery.
A 12-volt automobile battery is actually made of 6 cells connected in series. Each cell produces about 2 volts by the reduction of lead dioxide at the cathode and the oxidation of lead metal at the anode. This is a conproportionation reaction. The products of both the oxidation and reduction half reactions are lead-2 sulfate.
And so we can ask ourselves, is the reaction below spontaneous or non-spontaneous? And so we have copper 2 plus ions. And so copper 2 plus ions, we don't have to do anything to that half reaction. Zinc metal, we'll have to flip this one. And so if we flip it, that changes the sign. And so we should get 1.1 volts. And so that means it's going to be a spontaneous reaction, and we can use it to convert chemical potential energy into electrical energy. And again, please remember, oxidation occurs at the anode. Reduction always occurs at the cathode.
Spontaneous redox reaction between zinc metal and copper 2 ion can be harnessed in a voltaic cell to generate electricity. The cell consists of 2 half-cell compartments connected by an external circuit. Oxidation takes place in the anode compartment, in which a zinc electrode dips into a zinc nitrate solution. Electrons leave this compartment, travel through the external circuit, and enter the cathode compartment. There, reduction takes place at a copper electrode dipping into a copper nitrate solution. A salt bridge maintains charge neutrality in the 2 compartments. Let's zoom into the atomic scale and see how this cell operates. Here, at the anode, the site of oxidation, zinc atoms in the metal bar are in contact with the surrounding electrolyte solution. Each atom loses 2 electrons and becomes a zinc ion, which diffuses into the solution. The electrons given up enter the bar and join the flow of electrons up toward the external circuit. They travel through the wire and flow into the cathode, the site of reduction. When a copper 2 ion in the cathode solution makes contact with the copper electrode, it gains 2 electrons and is reduced to a copper atom, which deposits on the bar. Therefore, as the cell runs, the zinc anode becomes lighter, and the
copper anode actually gets heavier. Now, the salt bridge maintains charge neutrality. And so you can imagine that in the wire, you have negative charge going from left to right. And so you have to have a net negative charge going from right to left in the salt bridge. Now, because the salt bridge has both positive ions and negative ions, the way that happens is if you want a net negative going to the left, you can have positive ions going to the right and negative ions going to the left. So the salt bridge has to be charge neutral to begin with, so it has to have the same number of positive ions and negative ions. And each of these beakers has to also be charge neutral, has to have the same positive ions as negative ions. And so salt bridge just allows ion migration in solution. It prevents a buildup of charge in either compartment.
Charge flows continually as the cell operates. Negative charge in the form of electrons flows from the anode through the external circuit to the cathode. As negative charge in the form of anions flows from the cathode compartment through the salt bridge to the anode compartment, positive charge in the form of cations flows in the opposite direction. The oxidation of zinc metal in the anode combines with the reduction of copper 2 ion in the cathode to give the overall cell reaction. Under standard conditions, this cell generates 1.10 volts of electricity.
Now we can look at the cell notation. And in the cell notation, you always have the electrodes on the outside. So zinc is electrode, copper is electrode. Now a single line is used to separate out phases. And so the zinc electrode is a solid. The zinc ions are in aqueous, in a solution state. Here the copper again is solid, and then here you have copper ions in solution. Now the double line represents the salt bridge. And so this notation here represents the cell made from this reaction down here that we've been talking about. Now sometimes you also will include the concentrations in the cell notation next to the ions. Now typically if the concentrations are 1 mole per liter, because that's standard, they will not be included, and typically they'll only be included if it's not 1 mole per liter. And so here we have a different cell, and so we have platinum, cerium 3+, cerium 4+, fluorine minus ions, fluorine gas, and then platinum. And so we could ask ourselves, is platinum part of the net reaction or either the oxidation or reduction half reactions? And so the platinum is the electrode. Remember on the outside you have the electrodes. And on the left you have the oxidation. Remember on the left hand side is always the oxidation. And so the cerium 3+ is losing electrons, being oxidized to cerium 4+. On the right you have the reduction. And so the fluorine gas is gaining electrons to form the fluoride ions. And so the platinum is not part of either oxidation, reduction, or half reactions. It's not part of the net reaction. It's just where the reaction occurs. And so just like in the standard half cell, you have platinum is being used as the electrode, but it's not involved in the reaction. For this cell, it's the same thing. Platinum is not involved in the reaction. It's just where the reaction occurs. And so for this cell, we saw again left-hand side is oxidation, so we can write down the oxidation half reaction. Right-hand side is reduction. We can write down the reduction half reaction. We multiplied the oxidation half reaction times 2, so we had the same number of electrons. Remember, in the electrochemical reaction, you always have the same number of electrons in the oxidation and the reduction half reactions. It's always just about a transfer of electrons. And so for that cell, we'd have a potential of 1.26. And so we have a positive potential, and so that means this would be a voltaic cell. And so we can use it to convert chemical potential energy into electrical energy. So if you need to figure out if it's a voltaic cell or electrolytic cell, you have to figure out your oxidation reduction half reactions, look up the potentials of the half reactions, add the potentials to determine the potential for the cell. And again, if the potential is positive, then it could be used as a voltaic or galvanic cell. If the potential is negative, then it's going to be used as an electrolytic cell. So is a live battery or a dead battery at equilibrium? And so it's kind of an interesting question. And it turns out only dead batteries are at equilibrium. If your delta G naught is 0, or if your delta G is 0, that means you're at equilibrium. And remember our equation down here, delta G equals minus NFE. And so if delta G is 0, that means the potential will be 0. And so please remember there's two types of cells, a galvanic or a voltaic cell and electrolytic cells. And again, galvanic voltaic cells, you convert chemical potential into electrical energy. Electrolytic cells, you convert electrical energy into chemical potential energy. You should also remember that delta G naught, E naught, and K, they're all related. Given one, you should be able to determine the other two. Also remember your phone battery. When you're using your phone, it's behaving like a galvanic cell. But when you're charging your phone, it's behaving like an electrolytic cell. And so oxidation always occurs at the anode, reduction always at the cathode. I hope that was helpful.